Okay, today in IM2 we're going to talk about the properties of radicals. This is 4.1. We're going to spend a couple days on this so you can see that this is labeled day 1. So an expression that contains a radical sign is a radical expression. There are many types of radical expressions such as square roots, cube roots, fourth roots, and so on. And here's some examples of radical expressions. Okay, now the expression under the radical sign is the radicand. A radicand may contain numbers, variables, or both. It may contain one term or more than one term. So you might ask yourself, how many terms do these radicals contain? Okay, so if you look at the first one, this only contains one. Okay, this one has two terms, one term, one term, one term. Okay, so be careful. And an important thing to remember as we get farther into IM2 is that you have to solve the radicand before you can take the square root. Okay? All right, so the simplest form of a square root expression is when the radicand has no perfect squares other than 1. And we're going to explain what that means as we go through the problems. The radicand has no fractions, okay, and there are no square roots in any denominator. So those are things that you have to remember. Okay, so the product property of square roots, so the square root of a product equals the product of the square roots of the factors. So if I had the square root of 45, which is this one here, then I can separate it because there is a perfect square in there. I separate it into the square root of 9 times the square root of 5. So 9 times 5 equals 45. Then I'm going to split that, and it's going to become this. Now, you don't have to show all this work. I'm just showing you what you should be thinking. And therefore, this is 3 square root of 5. Okay? So for showing work, you would just show this and then go straight to that. But this is what I wanted you to understand. One helpful hint is when factoring the radicand, use factors that are perfect squares. For example, if the radicand is 18, you would factor it as 9 and 2. Some people might go, oh, 6 and 3. Nope, there's no perfect squares. So always think of all the factors so that you get them correctly simplified. Okay, so if we were going to simplify this, we need to remember that the square root of 24 is 2 times 12. No perfect squares there. 4 times 6. 4 is a perfect square, so that would be it. I could do 8 times 3, but 8 is not a perfect square, and neither is 3. So now I've got this. I'm going to split that. So this is 2 square root of 6, and I'm done. Okay, and it's going to show you that just like that, and there's your answer. All right. Okay, when we're given a bigger number, sometimes it helps to find a place to simplify it. So just factor it to see what the factors are. So I've got 128, and I know 2 goes into 128, so that would be 64. And right away I can see that I have a perfect square right here in 64. Now, I might not have thought of that right away, and I might have just kept going. Maybe I would have taken out 4 first, and I would have gone 32. And then I would have said, oh, 16. And then I might have thought of 4 times 16 is 64. But either way, I can see that this is 64 times 2, and then split it, and I get 8 square root of 2. Okay, so when you have variables, things are a little bit different. The first thing you want to remember is that this is a square root, and that anything that has any variable that has an even exponent is a perfect square. So here's how you solve these. So what I do is I divide out the positive. Okay, so I'm going to go x squared times x, because x2 plus 1 is 3. And then I just put the y4. Now I'm going to do the square root of each of these. So the square root of x squared is x, and the square root of y4 is y squared. And then I have that 1x left over, and that goes there. So there's my answer. Okay, notice that they don't put them in alphabetical order. You want them in your variables in alphabetical order. So this one's similar. We have the x squared x again with a y squared. We're going to pull out an x and a y, and we have one x left behind. Okay, if we had an x to the fifth, then I would do x to the fourth x1, 4 plus 1 is 5, and then I would have x squared x. So it's really important that you take out all of the extra x's. Anything over 2, any 2's can go out, okay? All right, when you have a number as well, then you have to think, what is this number? What are the factors of this number? Okay, so it's 2 times 24, 3 times 12, 4 times 8, but it's also 4 times 12. 12 also has a perfect square. So if you think about it a little bit, you'll figure out that this is 16 times 3, then just put the a squared b. Now we're going to take out the perfect squares. So we're going to take the square root of those two. The square root of 16 is 4. The square root of a squared is a. And then the 3 and the b stay behind. All right. Okay, now remember that I said before, if it's an expression inside, you have to combine things and simplify it before you can do the square root. So that means I'm going to go, oops, it's going to do it for me. So here we go. Do the calculation inside first. So 5 squared plus 12 squared equals 25 plus 14. Then you get 169. And then the answer is 13. Okay? Over here, this square and the radical and the, so it's going to show you this in a minute, the radical and the square cancel each other out. So you can just think of it as 3 minus x. So you don't need to worry about the absolute value because they tell you that they're not non-negative numbers. So these terms are only equal if you include the absolute value signs. But we don't usually worry about that. Okay? All righty. Okay, so the quotient property of square roots. The square root of a quotient equals the quotient of the square roots of the numerator and the denominator. So what you can do is you can separate it just like you did with the multiplication and then solve the bottom. Remember that one of the rules of simplifying radicals is there can't be a fraction in the radical and there can't be any radicals in the denominator. So both of those have to be solved for. So we're going to do some examples to explain that. Okay, so we have this problem and we're going to go through the steps one by one. So the first thing I'm going to do is use the quotient property, and that means I can divide my radical in half. I can divide the fraction that's inside my radical into two separate radicals. Then I can see that this is a perfect square, so that gets rid of my next problem, but I also want to factor this one. So here we go. Okay? So I can see that this is a perfect square. So now I'm going to take the, and then they're going to separate those using the product property. This is a step you don't need to write this. You can go straight from here down to the answer. And then we're going to take the square root of 36 and the square root of 25, and our final answer is this. Okay, we don't have any fractions in our radical, and we don't have any radicals in the denominator. Those are very important things. Okay, let's do another one. So for this one, we can see we have a perfect square in the denominator right away, but we also have the option of doing this division first, because this equals the square root of 64. So don't be afraid to check out to see if it can be simplified first, which might make your life a little easier. Okay? All right. Now, in your journal, this is on page 113. If you want to try this one by yourself, then go ahead and push pause and take a minute or two, and then come back and see how to do this problem. All righty. So first thing I'm going to do is separate it, and I'm going to simplify it at the same time. So this is 49, which is a perfect square, x squared x, over another perfect square, 64, and y squared is a perfect square. So this gives me 7x square root of x over 8y. And I'm done. Okay? Can't go any more simply than that. Now, when you have, be careful, this is asking for a cube root, which means we're trying to find something that's multiplied by itself 3 times to equal the number. And that's the only time that you can have a negative. So if you have an odd root, then you can have a negative inside. But the first thing we're going to have to do is factor this into perfect squares, because negative, if 135 is not a perfect cube, So I try to think of perfect cubes, and so 27. So I'm going to go negative 27 times 5 is 135. And I figured that out by factoring 135, and I took out 5, and that left 27, and I know that 27 is 3 cubed, which is a perfect cube. So that's how I discovered that. So now that I've got that, I know that negative 3 times negative 3 times negative 3 equals negative 27. So I can say that this is negative 3 square root of 5. Okay. So here's a caution. In the expression 5 square root of 5, these are not common factors. Do not cross-cancel them. This is completely simplified. So those are one of those fatal flaws that you have to watch out for. The first thing I want to do here is notice that these are cube roots, and then I also notice that there's a negative here. But remember, if this is odd, then we can have a negative inside the radical that can be solved. So first thing I want to do is factor out 192. So I'm just going to quickly do the math here and figure it out and see if I get a perfect cube, and I do. So I know I'm going to put the negative here. I'm going to put my cube, and this is negative 4 cubed equals negative 64. So it's negative 64 times 3. But I'm just going to write it like that. Then don't forget your 3. And then with the x5, I'm going to write x cubed, because this is a cube root problem, and x2. Because remember, x3 times x2 equals x to the 3 plus 2, which is the x plus 5 that we were factoring. So now we're going to do our factoring. I'm going to put the negative way over here so I don't forget it. The perfect cube of negative 4 cubed is negative 4, and the perfect cube of x cubed is x. And then what's left is 3 and x squared. And now I'm going to go negative times a negative, so my final answer is 4x cube root, don't forget your cubes, cube root of 3x squared. And that tells me that I'm done. Okay, over here, first thing I'm going to do, I'm looking for cube roots. So remember, 12 does not have a perfect cube, so don't try to factor it out. But 512 is actually 6 cubed. Okay, so keep that in mind. So I'm going to write that really quick just so I know where I'm starting. 12 has no cube roots, and we know that a to the 6 can be divided by 3, so we'll just leave it. This is 6 cubed, and then b3, b1. Okay, so now I'm going to factor out, got my cube root, and all that can be taken out on the top is a squared. Remember, a to the 6 divided by 3 is a squared. So that's what we get there. And the a's are all gone. And then down here, I can take out 1/6, and I can take out the b cubed. Okay? A cube root of b cubed is b, and then I'm left with this. Now, this is my final answer. So I could write it like this. But hopefully, right away you're saying, uh-oh, Mrs. Carter, this is not simplified. So what are we going to do here? Okay, stay tuned. we have further information. This is not done, okay, because we have a radical in the denominator and it can't stay there. So let's learn what to do. Okay, so in this case, you're going to do something called rationalizing a denominator. A quotient with a square root in the denominator is not simplified. To simplify these expressions, we have to multiply by the giant 1 to get a perfect square radicand in the denominator. So let's explain what that means. To create your perfect 1, you're going to take the denominator, you're going to put it in the denominator of your giant 1, and then you're also going to put it in the numerator. So if you look at this number equals 1. So in other words, we're creating an equivalent fraction. But the denominator has to match our radical in our denominator. Then we multiply them, and we get 7 square root of 5 over the square root of 25. Notice that we now have a perfect square in the denominator, which is what we were trying to do by having that be the same. Our final answer is 7 square root of 5 over 5. And now it's simplified. So let's go back and look at that problem that we just did. We had a squared, was it a squared? No, it was a squared cube root of 12 over 8b cube root of b. Now this one is a little different because we have a cube root on the bottom, which means we have to make b into a cube. So we're going to take and put the cube root of b squared as our denominator. This one would be the same. Okay, then we're going to get a squared cube root of 12 times cube root of b squared, whoops, don't forget your cube, over 8b, and we're going to squish these together, of b cubed, because the square root of b, cube root of b times the cube root of b squared equals the cube root of b cubed. So now we're going to squish these together up top, a squared cube root of 12b squared over, and now we're going to take the cube root of b again, we get 8b squared. And now that problem is complete. So that was a little more difficult than we thought, but it's totally okay. Tomorrow we're going to learn about something called conjugates. That's a J, yugates. And that has to do with when we have a term. Okay? So something like that would be a conjugate. We're going to discover how to use a conjugate to get rid of that in the denominator. But that's tomorrow. So have a good day.